Hello, I'm going to present SIMBIO-SYS, the instrument on board the BepiColombo mission that has been launched on October 2018 and will arrive to Mercury at the end of 2025. In this presentation, I will describe the scientific objectives and observing strategy of the instrument and then the future remote sensing of the Mercury surface. The top-level organization of the team has a 1 PI, 5 co-PIs, 1 technical manager, and the industrial prime that is Leonardo in Florence, Italy. The team is very large, composed by 60 co-investigators, 25 associates, coming from 12 different countries. Here you can see a picture of the instrument that is composed by 3 optical channels sharing the main electronics and the power supply. We have the stereo camera STC that will perform the global stereo mapping of the planet with a pixel scale of 60 meters. Then we have the visible and near-infrared spectrometer Vicky that will perform the global mineralogical mapping with a pixel scale of 120 meters. With a spectral range of 0.4 to 2 microns and a spectral sampling of 6 nanometers. Then we have the high-resolution channel that will perform high-resolution observations of selected regions, with the pixel scales in between 6 and 12 meters. The principal operations are briefly described here. The primary target of the instrument is to provide the global coverage of the planet with the 2 channels, the spectrometer Vicky and the STC, the stereo camera. Then there is the high-resolution camera that is the target-oriented instrument that will observe selected regions and can operate all over the orbit of Mercury around the planet and the spacecraft around the planet. And all the SIMBIO-SYS channels can operate at the same time in parallel, allowing a very good flexibility. 50% of the data volume, the entire mission, is allocated to SIMBIO-SYS, corresponding to 750 gigabit per year. Most of the data will be compressed by a factor 7. The NASA messenger already provided the global coverage of the Mercury surface, observing for the first time several regions and features, raising new questions about the planet origin. According to this data, SIMBIO-SYS shall address the main following topics: the global contraction of the planet, the composition variability of the surface, and the nature of the hollows, then the ice deposits in the polar regions. Here you can see the coverage of the high-resolution images acquired by Messenger that correspond to 2% of the surface, mainly on the northern hemisphere, with the spatial resolution better than 12 meters. In the case of high-resolution camera of SIMBIO-SYS, we will cover 20% of the surface in the pixel scales between 6 and 12 meters. The digital terrain model provided by Messenger are based on the laser altimeter observation that are focused only on the northern hemisphere, providing an average grid size of the DTM of 665 meters, the same average grid size of the global multi-image DTM provided by USGS using all the images acquired by Messenger. The STC of SIMBIO-SYS will provide the global DTM with the grid size better than 120 meters. The spectrometer on board Messenger was a point spectrometer with a pixel size of few hundred meters, working in the spectral range of 0.3 to 1.5 microns. In the case of SIMBIO-SYS, the spectrometer is an imaging spectrometer providing hyperspectral images with a pixel size of 120 to 480 meters and working in the spectral range of 0.4 to 2 microns. In the case of the global coverage, the data will be binned in order to provide hyperspectral images having 500 meters per pixel. In the case of target observation, in the second half of the nominal mission, we will use the maximum spatial spectral sampling. The polarized observations are very important, and it is a primary objective of SIMBIO-SYS. The spectral range of Vicky is the right one to observe the 4 diagnostic absorption bands of water ice. Then the spatial resolution of 200 meters per pixels is enough to resolve the ice spatial distribution along penumbra boundaries within kilometer-sized craters. The BepiColombo orbit is right to achieve the optical spatial coverage several times, and so allowing redundancies of the observation of the polar regions. The 2 cameras will provide the context high-resolution images and DTM of the ice deposits in the polar regions. We are working on the observing strategies, and we started from the stereo camera. In the future step, we will provide also the observing strategies of the other 2 channels. STC will work only around the aphelium in 2 different observing modes: the stereo mapping, that will provide the global stereo coverage of the entire surface, and working in the first 2 aphelium in the first half of the nominal missions. Then there is the color mapping mode that will work in the second half of the nominal mission, performing images with the 4 broadband filters. Here you can have an idea which are the ranges of the integration time and the repetition times. As STC has the stereo acquisition based on the push frames, we have to define the repetition times in order to get the right frames and then the mosaicing to provide the final images of the surface. In the case of the color mapping, the integration time and the repetition times are different, as it depends from the wavelength coverage of the filters, and then because the filter size are different on the detector. And so the frame has a different size. Recently, we performed the first target list, and the scientific team of SIMBIO-SYS selected 400 targets according to few parameters as the incident angle, emission angle, spatial resolution, and so on. Here you can see the distribution of these 400 targets all over the surface in the 2 polar regions. The next step will be to check the feasibility in terms of operation and observing strategy. At the same time, we are working on the simulator in order to simulate the observation of the 3 channels, and so to define the performances of the 3 channels and the signal-to-noise ratio that will be able to achieve according to the different integration time and the different observation parameters. The simulator is based on the radiometric model that is ready. It takes into account the transmission characteristics of the optical elements, the detector characteristics, and then apply the Apke model to the surface in order to get the surface properties as the grain size and the porosity. This radiometric model can be used for the 3 channels. Here you can see the observing strategy and the simulator applied to STC. On the left, you can see the simulator results for the stereo mapping, and so the signal-to-noise ratio that will be always greater than 140. On the right, you can see the signal-to-noise ratio for the 4 different filters that will be different depending from the wavelength coverage and the integration time. On both modes, we will work around the aphelium. In parallel to the simulator and the radiometric model, we have to simulate also the acquisition of the stereo pairs that both cameras will be able to perform. And so, using the SPICE kernels, we will be able to define the geometry acquisition of both cameras and to define the camera matrix, the projection matrix, in order to initialize the photogrammetric process. In the case of the high-resolution camera, it could be quite critical to define the best observing parameters, as we can we can acquire stereo pairs only for few selected regions. According to the data already acquired by Messenger, we be able to emulate the 3D model of the chain of the surface in order to simulate, to compare the simulation with the real observations. Here you can see a few images, a few simulation performed at 4 different latitudes and 4 different incident angles. According to this simulator, we are able to plot the preliminary results. In this case, you can see the root mean square error of the vertical accuracy of the DTM as a function of the incident angle. In this case, you can see that the best vertical accuracy will be achieved with the incident angles of 72 degrees. This is in the case of well-contrasted regions and features. Future simulation will provide the output and so the parameters of the observation even for other regions and for other values of the incident angles. This is only the preliminary steps. Future work will be to provide the observing strategies and the simulator results for all the 3 channels. Thanks for your attention.